Guys, I have another example here for you, and now we're looking at something that the AP test might do to you, and they're giving you function has derivative for all real numbers, and then they give you values like f of 0 to be 4, f prime of 0 to be 5, f double prime of 0 to be -8, and f triple prime, or the third derivative, at 0 to be 6. They want you to do two things. One, we're getting the third order, so remember, third order, you mean your degree has to be 3, right? And then we want to use this. This is a little bit new. I haven't done this yet, to approximate f of 0.2. So almost like when we were doing approximations with equations of the tangent line, which is basically the same thing. It's just a first order. But now we're going to third order. And then we're going to do a second order polynomial for the first derivative, which is a little different, at 0. And use it to approximate f prime. So notice the difference. One, we're approximating f of 0.2 and f prime of 0.2. Okay, so when you do this, right, they already gave you all your derivatives. So for the first one, A, my polynomial is going to be, right, you always start with the first value, like f of 0, so that's 4, plus 5x, right? I'm getting the 5 from here, and it's the first degree, so 5x. If we stop there, that would be the linear approximation that you would have, where you have, it's 0, 4, so it's 4 plus 5x, if you solved, right? And that would be the tangent line that we would use, but now we're using more derivatives to do these approximations. So then I'm going to have plus -8x squared and divided by 2. Factorial, which is really 2, but I'll leave the factorial so you see it. And the last one is plus 6x cubed over 3 factorial. We could clean this up a bit, right, to make it a little bit easier for us when we plug in. So think about it. 8 divided by 2 is going to be 4x squared, right? And 6 divided by 3 factorial is 6, so that's just 1. So it looks like that. So that's the first part. Now what we want to do is approximate f of 0.2. So just like when we were using tangent line, we have this ability to approximate. What I'm going to do is I'm going to plug in the 0.2 to get my approximation. All right. So this gives us an approximation of 4.848. Okay, so that would be f of 0.2. We know in this situation is approximately 4.848. Okay, so that's for part A. Now for part B, okay, we're not changing too many things because we want to get the second order. Now it's a little bit different, all right? Why is this different? Okay, the second order of the first derivative. And then we're going to approximate f prime of 0.2. So the things you need are first derivative, second derivative, and third derivative. You don't need this anymore, all right? Because we're doing our approximation now for the derivative. So I'm starting, just like here, I always started with f. Now that I'm doing a Taylor polynomial for the derivative, I'm starting at f prime. Okay, so still same idea, right? So we're doing a polynomial for f prime, and in this case, second order. So I want it to have end with an x squared, end with an x squared. So you don't need f of 0 anymore. You need f prime of 0, and that's going to be 5, okay? Then minus the 8x, right, divided by 1 factorial, which is just 1, and then plus 6x squared divided by 2 factorial. If we clean that up, so 6 divided by 2, 3x squared. So there's my second order polynomial for f prime of x, not f of x, okay? And then in this situation, we are just plugging in our 0.2 for this function now to get the approximation for f prime of 0.2. So 5 minus 8 times the 0.2 plus 3 times 0.2 squared. So this gives us an approximation of 3.52. Okay, so you can see a couple different things that we can do with these Taylor polynomials now are just like when you're doing approximations or linear approximations like we did before with tangent lines. Now we could do them with Taylor polynomials, whether it's third order, second order, and you could even approximate derivatives. You see now, works out pretty nicely for us.